And welcome to 9-3 Transforming Functions from Way Happy Studios here in Livermore. This is Mr. Meyer, and let's do one of our favorite things, right? We love to talk about transforming a graph. Once we learn a graph, we like to talk about how you move it around, and this is something you've seen now a bunch, so hopefully it's making sense, right? So the first thing you want to notice is that, again, with any graph right here, right? Anything that's happening to the x value, we're going to do the opposite. Notice in here when it's inside, we're going to move it left and right. So when you add to the x and the x only, that's going to move a graph left and right. And you do the opposite. When you have a negative on the inside, that's going to be kind of weird. It's going to flip it across the y-axis instead of the x like we're used to. And inside here, probably the hardest one, when you multiply something to the x, that's going to be your horizontal stretch or compression. Now, you have to be careful. The number that they're doing, if it is, like normal, if you see something that's bigger than 1, it's a stretch. If it's smaller than 1, it's a compression. But here's the big trick is we're going to flip whatever's in there. We're not actually going to flip it. We're just going to flip it in our brain and see if it's bigger than 1 or smaller than 1, and we'll talk about stretch or compression. So make sure you got all that down. Inside or happening to the x is always bizarre. Outside happening to the entire function, that's always good news. You just do it what you do, right? On the outside, we're going to move you up and down. Or if you put the negative on the outside, we're going to flip you over the x-axis. Or if we have a multiplier, that's going to just be the same thing. It's going to be bigger than 1, it's a stretch, and smaller than 1, it's a compression. Those are called verticals. Now, there's one super important thing I like to talk about if somebody throws this stuff at you. You always got to remember to stretch before you slide. Every time you go to the playground, you should always stretch before you slide because you don't want to get hurt. Now, what does that have to do with this? These I call my stretches because there are multipliers. So if you are going to do any of the multiplying first, that should come first. And then left and right and up and down, those are your slides. So make sure you always do your stretches before your slides. That's going to be later on an example, but that's something you need to hold true for a long time now. So now we got our stretches and our slides all good. So here comes example 1. First thing you want to notice is we got a graph. And again, piecewise function, so remember it's got 2 parts. One part of this graph is that we have a negative slope if your x's are less than 0. We have a positive slope if your x's are greater than 0. Notice it's a parabola and a line. So there's the 2 tricks right there. Now they want you to give me a rule. In other words, can you rewrite this equation if you stretch it by a factor of 3? So just a quick stretch by a factor of 3. Now notice it's a vertical stretch. That's the good news. That means we're going to take a 3 and we're going to multiply it to all of f of x. In fact, the whole entire function we will multiply by a 3. So not a big deal. If I'm going to do that, I'm going to go ahead and take g of x right now, I'll call it, because it's a different function. And I'm just going to multiply the function by 3. So I will take whatever was there, and I will multiply it by 3. And I will take whatever's here, and I will multiply it by 3. And that will now give us a vertical stretch of a factor of 3. So to kind of clean that up a little bit, I will call that negative 3 halves x. And I will call this one 3 halves x squared. And there's your new function. Now the weird part, you got to worry about these constraints again, right? This tells you when to use each one. If you do a horizontal, a left-right shift, that's going to change those constraints. But if we're just doing a stretch or a compression, and we're not sliding left or right, then we're not going to worry about those constraints. So I can leave them alone. So I have if x is less than 0, I still want you to use the top one. If x is greater than or equal to 0, I want you to use the bottom one. And we can talk about that more in class. But make sure you understand left and right shifts, that's what affects the x. That would change those constraints if we had to. And there it is, finished and happy. Why don't you try one of these? Thanks. Very nice work. Now this looks a little overwhelming, I agree. So before you start freaking out, kind of look at this. If you have to pause it and read it, do that. But I want you to think about one thing. If you think of a graph being stretched horizontally, left and right, then notice the y-intercept wouldn't change. The only thing that would change are these x-intercepts right there. They would move, but y-intercepts wouldn't because you're stretching horizontally. You're making the graph wider. You're going to change the x-intercepts. You're not making it taller. That's why the y-intercept isn't touched. Now look at the next one where it says a vertical stretch, right? Now you're making the graph taller. That's definitely going to change the y-intercepts, but making something taller doesn't change the x-intercepts at all. So that's something you got to keep in mind when we ask you to do intercepts. If you reflect something across the y-axis, well then notice these guys are going to jump over here and switch spots. So your x-intercepts are going to have sign changes while your y-intercept doesn't care because you flipped it across the y-axis. And last but not least, look at your x-axis reflection, up and down, opening up or opening down. Notice that's going to change your y-intercepts, but it won't do anything to your x's. So just kind of nice to know. You can kind of logically think about it if you just think about what's going on and envision a parabola or something in your head, and you would be able to tell which is which. Well, here we go. Let's find the x and y intercepts for these bad boys. Now, if you remember way back in, I don't know, probably Algebra 1 or something, and we hint to it every now and then, we have to find the x-intercepts of a graph. The easiest way to find the x-intercepts is just to make y equals 0. So remember, f of x is just y. So 0 equals negative 2x minus 4. Solve that for me. You're like, all right, I'm going to add 4 to both sides. And I'm going to get 4 equals negative 2x. And I'm going to divide by negative 2 and get x is negative 2. That's our x-intercept. It's best if you write it as a point. You write it as the point negative 2, 0. So there's your x-intercept, right? That's where the graph crosses the x-axis. Now, if you want to find the y-intercept, you're like, sweet, I will do the y-intercept. Well, the little trick that you learned was make x is 0. It's usually pretty easy. I plug in x is 0, so I got y equals negative 2 times 0 minus 4, which is just 0 minus 4, which is negative 4, and that's my y-intercept. And I like to write that as a point. X is 0 and y is negative 4. Now, that's the x-intercept and the y-intercept for the f of x function, the original function, right? Now let's talk about the f1 half x. So the first thing you want to do is figure out, they want the x and y intercepts, and you want to figure out what kind of translation is going on here. Well, it's inside with the x, so I know that's opposite, right? So something weird's going on. Okay, it's a multiplier. That means it's a horizontal stretch or compression. So if I look at that, I'm like, all right, if I flip it in my brain because of the opposite thing, it's a 2, that means it's a stretch. So I know that this is a horizontal stretch of 2. Well, now it's nice. If you want to find the x and y intercepts, and you've already found them on the original, then on this one, we have to think of a horizontal stretch. And what happens? Well, the y-intercept stays the same, and the x-intercepts will get this horizontal stretch. So our new x-intercepts, or the x-intercepts for this graph, would be, multiply it by 2. Negative 4, 0. That's our new x-intercept. And our y-intercept, he's just going to stay the same. So he will be 0, negative 4, because he did not get stretched vertically, he got stretched horizontally. So making him wider made his x-intercepts farther away from the origin. Awesome, right? Piece of cake. So if you can just remember x and y intercepts and think about what the graph does, then this isn't so tricky. Now this other one's going to look kind of weird, but we'll enjoy every minute of it. So let's see. First thing I notice is you want me to find the x-intercept of the original and the y-intercept. So remember my little trick that I've always known. If you want to find an x-intercept, you make y as 0. If you want to find an x-intercept, you make x as 0, because that's where it's crossing those axes. So for this first guy, if I make y as 0, it would look like this. 0 equals x squared minus 1. I would move the 1 over and get x squared equals 1. I would square root both sides and get plus or minus is x. Those are our x-intercepts. Sorry, plus or minus 1 is x. So we have an x-intercept at 1, 0. And we have an x-intercept at negative 1, 0. So those are our x-intercepts. Now our y-intercept. Piece of cake, make x is 0, so y would equal 0 squared minus 1. I think we all say that is y equals negative 1. And to write that as points, we would say 0, negative 1 is our y-intercept. So there's our y, there's our x. Remember, that's on the original. That is for the original graph. So now let's do it for the stretched one, or whatever the heck's going on. Ooh, look at that. a negative x in there. That means somebody is stretching, right? Or I'm sorry, flipping it. And they are flipping it over the y-axis. So this one is flipped over the y-axis. Now, if you think about a y-axis flip, your y-intercept again will stay exactly where it is. So 0, -1 for my y-intercept. But my x-intercept, they will change their signs. So the x-intercepts will get a sign change. Well, that's kind of funny on this one because look, the first one would change sign, so it'd be -1, 0. And the other one would change its sign, just the x part, right? And you would get 1, 0. And there is your flipped over the y-axis. Nice. Let's see if you can read some shifts and tell me which way things are going to change. All right, nice work again, and you are on a roll. Now let's see what we got here. This example 3 is going to try to crank it up a little bit by saying, let's do everything at once, or let's do 2 shifts or whatever, and see if anyone panics. So here's my advice. Remember, you stretch before you slide, right? Remember the stretching before the sliding. So we're going to make sure that we do all that first. All right, here we go. They want us to graph this thing. Now again, you got 2 ways to attack this. You could graph and then move your graph, which I think is a good choice. If you remember all your translations, you're looking at this first guy and you're like, all right, it's a parabola. All right, you're like, I know it's a parabola. I know it's right 2 units, so right 2. So boom, there it is. And a little tricky here. I need another point on a parabola, right? Remember, it has this line of symmetry. And what happens is we need 1 point on the side, so then we can put it equidistant from the line of symmetry. So I don't know, let's pick something easy, like maybe x is 0. So when I plug in x is 0, I get 0 minus 2 is -2, squared is 4. 4 times a third is 4/3, or 1 1/3, or whatever you want to call it. So it's a little over 1. Boom. And there it is. If you go right 2 units now, you should be the exact same point. And there's an idea of what this parabola looks like. And it's graphed. Now, they want us to graph g of x. So in other words, they want us to graph this guy. Well, he's the original one right there, f of x. He's that one. But he's got a multiplier of 2. So let's see, to the whole function, that's a stretch of 2. So he's going to be steeper. If you want to think in the world of y-intercepts going up, right? Going to multiply the y-intercept by 2, so it'll be 8/3 now, or whatever you want to think of. And then you're going to do a down 3 shift, then you're going to move everybody down 3. So what I would probably do on this thing is I would take our original equation, like this, and I would do a multiplier of 2 to that. So multiply this whole thing by 2. Because that's what it says, right? Take the entire function and multiply by 2. Well, that's kind of not too bad because all you have is these 2 guys. It's not distribution because there's no plus or minus or anything. It's these 2 things are multiplied together, so that's one term. So when you multiply, you get 2/3 x minus 2 squared. So now it looks like that, right? That is our multiplier of 2. That's if somebody just told us to do 2 of fx. We just did, right? But now they're saying do a -3. So remember what that means. Now let's do our slide. We take the entire function that we had and we move it down 3. We take the whole function and we just put a -3 on the back end. And that is our g of x, right? That's what we want to graph. So I would probably do it the same way. I'd be like, all right, I know it's a parabola. I know it's right 2, down 3. So I'm going to go right 2, I'm going to go down 3. And then all I need is one more point on this graph. If you know one, great. Like plug in x is 1 or whatever. I'll probably do x is 0 one more time. Just to show you we should get what we think we get. 2 times the 4/3 is 8/3, but then we have to -3. So we'll see how goofy it looks. Plug it in the 0, I get -2 squared is 4. Multiplied by that, I get 8/3 -3. Now, I don't know what that is, so I'm going to change this to 9/3. And notice I get 8 minus 9 is -1/3. So down 1/3 would be where this bad boy is. Copy it on the other side. And lo and behold, you have just graphed such a tricky graph, right? Notice it's vertically stretched somewhat by a factor of 2. Notice the whole graph has been moved down 3, and we're feeling pretty darn good. Well, let's go one more step then. If we can do it there, we can do it in a word problem. This is a real life kind of problem, right? You go anywhere, you see them offer prices for so much, and this is saying that Coco's Coffee has a pricing scale that if you buy 0 to 3 pounds of coffee, we will charge you pretty much $9 a pound. Now, if you buy more though, if you're willing to buy 3 to 6 pounds of coffee, we're going to drop that price down. Instead of $9 a pound, it's going to be $7.50 a pound, but we're going to add $27, and you know, that's all for the math, right? Someone's figured that all out and how much it is. So this just represents how many pounds of coffee you're going to buy and how much it's going to cost you. So there it is. Then somebody realizes that, hey, it's kind of expensive to have a store. If we could have a holding tank somewhere, a warehouse, let's offer people a discounted price of 1/3 if they buy online. So we need a new scale, right? We need our online pricing. This is our pricing here in the store, but we need online pricing to see what happens. So what we're going to have to do is discount it by 1/3, give them 1/3 off. In other words, they would pay for 2/3. So if you get 1/3 off, you're paying for 2/3. So we're going to call that a vertical compression of 2/3. Now 2/3 because of the fact that they will still pay 2/3 of the price. But look, we can't just do it because now we have to ship it to them. Shipping's always going to cost us $2.50 apparently. So why don't we add that onto the customer's price? Now that's just going to get added on to the back end. So that is just, you know, kind of like a up 2.5. So this is going to be an up 2.5 shift. So remember, or a slide. So remember, we're going to want to do our compression, our stretching, before our sliding. So piece of cake. I am going to take this equation, and I'm going to take the 9W, the 27 plus 7W minus 3, and the 49.5 plus 6W minus 6, and I'm going to do a multiplier. My multiplier will be 2/3. So 2/3 to this guy, 2/3 to this entire guy, and 2/3 to this entire guy, and that will show us a vertical compression of 2/3. And now that we've done that, I mean, we could clean it up a little bit if you like. If I multiply it by 2/3, then what will I have? I will have 6W for this guy. For the next guy, I'll have 18 plus 5W minus 3. And the last one, if I multiply it by 2/3, it's going to be 33 plus 4W minus 6. So I just cleaned it up. All I did was distribute the 2/3 through, so you would see it again. That way you go, oh, okay, that's a little cleaned up. You know, it looks a little prettier from the last one. And now look at our last step. We need to add that $2.50 shipping charge. So this guy's going to get a $2.50 added to him. This guy's going to get a $2.50 added to him. This guy's going to get a $2.50 added to him. And now we have our new pricing for our online store. We'll call this pricing for the store. So online, we'll call it O. Maybe that's a gross letter to put in a variable. So I'm going to leave it as W's. Pricing for online though, we will call it 6W plus 2.5. We will call this one, if you add 18 and the 2.5, you know, you should get 20.5 plus the 5W minus 3. And last but not least, 35.5 plus 4 times the W minus 6. And now talk about our constraints. Their weights won't change, right? We're still doing this. We're not saying, hey, they have to buy more or something to get these prices. We're just saying that if you do this online, you will get a cheaper rate, and therefore we will leave these constraints right here about when we use which pricing. And that's it. That is how we figure out pricing for our online store or are in the store. Nice work. I'll see you tomorrow. Have a great day. Stay happy.